Our paper is entitled Real-Time Multi-Diver Tracking and Re-Identification for Underwater Human-Robot Collaboration. The motivation for this paper stems from the fact that underwater autonomous vehicles frequently work with teams of human divers, as shown in the image below, where we have 3 divers and a robot in the center. Humans and robots work together underwater on a variety of tasks, including data collection, ecological mapping, and shipwreck investigation. And during these tasks, it is often desirable for the robot to be able to identify the different humans. For example, to identify a team leader, to distinguish between team members and any other divers that may be present, to return to a specific person after completing a task, or to follow a specific person. So this is an open problem, and some challenges include the poor visibility conditions underwater. As evidenced in this photo on the right, we see the light refraction, absorption, scatter. Also, similarity in divers' appearance. So these 2 divers on the right are wearing very similar gear, and it's hard to distinguish between the 2 of them. We also need to re-identify divers who disappear from the robot's field of view and then later reappear. And re-identification is a really difficult problem on the ground, and it becomes even more difficult underwater because of the inherent challenges in underwater vision. Our approach in this paper is to apply ideas from multi-object tracking to the underwater domain. We use the tracking by detection paradigm with a convolutional neural network to detect divers that runs in real time. We extend the state-of-the-art real-time trackers, SORT and Deep Sort. We'll talk more about those trackers in a moment. And we extend them to first utilize diver-specific appearance metrics for tracking and re-identification. Second, to allow tracks to persist even after long absences. And third, to recover from certain re-identification errors. There's a lot of related work in underwater computer vision and diver detection that I don't have time to talk about, but I will briefly mention the related work in multi-object tracking. This video is a depiction of SORT, or Simple Online Real-Time Tracking, in action. And we can see that it works pretty well. It's a very simple, lightweight tracker that uses only intersection over union and a Kalman filter that models location to match detections to tracks. The main issue with SORT is that if a person disappears briefly, whether because of an occlusion or some missed detections, SORT will not be able to re-identify the person because it doesn't keep track of what people look like. And that's where Deep Sort comes in. Deep Sort adds a deeply learned appearance metric, and this allows it to re-identify people even after occlusions or missed detections, and it still is a very fast algorithm that it runs in real time. So I'll walk really briefly through how our method works. The first thing that we do when we try to match a detection to a track is do IOU matching. So in this case, if we receive frame T and our diver detector returns this white bounding box, if we want to do IOU matching, we'll look at the previous frame, frame T-1, and we see that there is a detection for track 1 in the frame, which is denoted by this 1 in the upper right-hand corner of the bounding box. So to do IOU matching, we look at track 1's detection in frame T-1 and take the intersection over union of that bounding box with the detection bounding box in frame T. And since these bounding boxes are really similar, their IOU is very high, and we can match the detection in frame T to track 1. This is a really good first step to take because it's extremely fast, and our tracker really does need to run in real time. However, we won't be able to match every detection in this way. So for detections that we can't match with IOU, we want to calculate the cost of matching the detection to each of the existing tracks. And that cost is going to be based on both appearance and location. So how similar is this detection in terms of appearance to all of the existing tracks? And how similar is it in terms of location to all of the existing tracks? So how we model a track's location is with a Kalman filter that predicts the XY center coordinate of the track's bounding box. So in this case, if we're looking at the detection in frame T and we want to see how similar it is in location to track 1, we ask track 1's Kalman filter what the center XY coordinate would be. And maybe it gives us back something like this mark shown in pink. And then to determine how similar the detection is to track 1, we just look at the distance between the detection center XY coordinate and the center XY coordinate that we got from track 1's Kalman filter. Of course, we also want to look at the appearance similarity between a detection and a track. We do this by creating a vector filled with various appearance features that can satisfactorily differentiate between divers, but are also relatively robust to changes in both lighting and diver position orientation. For more information about these features and why they're good for identifying divers, please see the paper cited below. In summary, these features include the average color distribution, shape approximation through image contours. The image contour example is shown in photos to the right. Also shape approximation through convex hull and hue image moment and variance. So to quantify the appearance similarity between a detection and a track, we simply take the cosine similarity between their respective appearance feature vectors. So the final step for matching detections to tracks, we create this cost matrix. For example, this is what a cost matrix might look like for matching 2 detections to 4 different tracks. The Hungarian algorithm can then match detections to tracks in a way that minimizes the cost. This is a really common strategy for tracking algorithms. To get more details about how we actually compute the cost numbers, please see the methods section of the paper. But I will point out that we do set an infinite cost for any matches that are extremely dissimilar in either location or appearance. So if a detection can't be matched to a track with a cost that is less than infinity, we will simply create a new track for that detection. The other thing that our method is concerned with is the problem of missed re-identifications. So if a diver leaves the scene and then when they reappear, their initial appearance might not be similar enough to successfully re-identify them. So we might create a new track for them, even though we should re-identify them. So to hopefully account for this sort of situation, for the first 15 frames of a new track, we also check to see if maybe we should have re-identified this person instead of creating a new track for them. So what we do is compare the new track's appearance to the appearance of all the tracks that haven't been seen since the new track was created. And if over these first 15 frames we start to notice a lot of similarity between this track and an older track, we do re-identify. So this can be shown in the sequence of frames here. We have a diver being identified as 2. The diver kicks up some bubbles, we miss some detections, and when the diver is detected again, they seem pretty different and they are not re-identified correctly as diver 2. However, over the first few frames, the algorithm keeps on comparing this new track to the previously existing track 2. And finally, after a few frames, there's enough similarity that it realizes that this person should in fact be diver 2. So we evaluate our method using standard multi-object tracking or MOT metrics to compare our tracker to sort and deep sort on videos of underwater human-robot collaboration. And we're specifically interested in the MOT identity metrics, so identity precision, identity recall, identity F1, and this tells us how well we're identifying divers. We test 8 different videos, 6 are from the ocean, 2 are from pools. You can see 2 examples of ocean videos on the right, or on the left rather, and in the center, and on the right is an example frame from a pool video. So this is one illustration of results for the identity F1 score, where of course F1 is a blend between the identity precision and identity recall over the 8 videos. Our method we call diver sort, and that's in green, and we can see that it does consistently outperform the other trackers for these underwater videos. Our full table of results, as well as an in-depth discussion, can be found in the results section of the paper. We did find a strong positive correlation between the detector's performance on a video and the tracker's performance on a video. This is a well-known artifact of tracking by detection. And importantly, this means that in videos where the detector performed really poorly, the trackers were also performing really poorly. We ended up with an end-to-end processing rate of 9.8 frames per second on a CPU, which is really great because this method is then real-time capable for a robotic platform. Here's a brief video. Unfortunately, this video has a low frame rate, but it does show results of our tracker tracking divers with identity 1 and 3, and also re-identifying diver 3. So our conclusions is that our method is an improvement for multi-diver identification in underwater scenarios. To improve our tracker, the first thing we want to do is look at improving our detector. We also want to develop a method that can flag poor detection and/or tracker performance in order to safely deploy this tracker in the field. We'd also like to thank our sponsors listed below and thank you for your attention.